We have a bunch of stuff to do here, so we need to go ahead and get started. No more messing around. And we're going to do non-inertial reference frames. So this is part of my classical mechanics series. The link to the whole playlist is down below. Let's just start with an example. So imagine that you're in an elevator. You've probably been in an elevator before. And that elevator is just stationary at rest. And you take a ball and you toss it in the air. And it goes up in the air and it comes back down. And you catch it. And you want to find out how high it went and all this stuff. Everything's fine. Normal physics. Even if the elevator is moving at a constant speed. Normal physics. You wouldn't even tell if it's moving or not moving. Okay. However, what if the elevator is accelerating up? Now there's two ways you could look at this elevator and the ball. If you were outside the elevator, you could look at the motion of the ball and just use your normal Newton's second law. But what if you're in the elevator? Well, now the ball is going to have a different acceleration compared to in the elevator than out of the elevator. And one way we can deal with this situation, Newton's second law doesn't work, right? Newton's second law says the acceleration of this ball should be negative 9.8 meters per second squared in the y direction, but it's not. So we can fix this. We can fix this non-inertial reference frame by adding in fake forces. So I'm going to show you how to do that with a linear acceleration frame, and then I'll do it for a rotating frame. Now, I'm not going to do linear accelerating and rotating at the same time because I'm not crazy, okay? And I'm going to do this in a little bit different way than most books do it because most books get a little too out of control. So we'll just kind of do it. But don't worry, there will be Python at the end. Okay, so how do we deal with this situation of an elevator with a constant acceleration? Let's start off with the following situation. Suppose I have a stationary reference frame right here, and then I have another reference frame. I'll put it right here because it doesn't really matter. It started at, and this is the S prime, and this is the S reference frame if you want. No, I'm not going to call it that. I'm going to just call it the X prime and the X because I want to use S for something else. And so this is an inertial reference frame, and this is not. But this is moving with an acceleration that way. In any particular direction, doesn't really matter. It has an acceleration A. Now I can find the location of an object in my stationary frame, and that's the vector r. And then I can find the vector with respect to my accelerating reference frame, and I'll call that r prime. Now this violates my rules of you can only wear one hat, right? My rule is you can have one hat. You can have a vector hat, you can have a prime hat, you can have a dot hat, but you can't have two, but we're going to do two hats, maybe even three, and I'm sorry, multiple hats. Okay, so if these two start at the same position at time t equals 0, then I can write this vector r prime. I can say r prime, the vector r prime, is going to be the vector r minus 1/2 a t squared, right? They start at the same point at time t equals 0. This is accelerating away, so that tells me the difference between those two. Right. Okay, so now let's just take the derivative twice. Let's take the derivative once, let's take the derivative of this, and here's my 3-hat rule. I could write this as the velocity, so let's do that. If I take the derivative of this, I get v prime. It's going to be the derivative of r, which is v. That's the velocity of the ball. And now I take the derivative of this, and I get minus a t. But minus a t is the velocity of that frame. Okay. Now if I take the derivative again, I get a prime is going to be the derivative of the velocity, which is a, the actual acceleration, minus, oh wait, I did that wrong. Yeah. Because that's a. So let's call this as for the frame. So it's going to be a minus as. Now, I know that is the acceleration based on real forces. This is the acceleration based on the real force plus that acceleration of the frame. So if I use this in Newton's second law, I can say ma prime equals ma minus mas. So those are due to real forces, and that F fake is negative m times the acceleration of the frame. And that's one way to make that work, right? So now if I go back to the elevator is accelerating up. I can add a fake force that's the mass of the ball times the negative of the acceleration. So a fake force, it feels like there's an extra force pulling it down. You can expand this up to really far. You could say, okay, this is the Einstein equivalence principle, right? It says that there's no difference between gravity and an accelerated frame, and that's the same idea. Okay, but that's pretty easy. What if you have a rotating reference frame? Now, it gets a little bit more complicated. Okay, so let's imagine a rotating reference frame, but we're going to make it a special case. Let's say that we have the S frame is right here, and then and I can locate some object right here with the vector in polar coordinates. It's going to have it's going to be the vector r, but that's going to have an r and a theta value to it. And then I have an S prime that's rotating with respect to that. And so this is rotating at an angular velocity omega. So this angle right here is omega t. So at t equals 0, they're right on top of each other, but it's rotating. Okay. So this is going to have an r theta value, but in the S prime, so in the S, it has the coordinates r theta. In the S prime frame, it has the coordinates r prime theta minus omega t, right? Because I have to subtract that little tilt angle right there to get the new thing. But you'll notice that since the two axes have the same origin, they have the same distance from the origin. So that means that r prime is r. So these are not vectors. These are your coordinates, right? R and theta coordinates. So, but the r and the r prime are the same. That's important. And then theta prime is theta minus omega t. Those are my relationships. So we can go ahead and look at the derivatives, right? I want to look at the derivatives in polar coordinates. I'm going to have to write that down. But let me go ahead and say, let me put this over here. R prime, let me make it a little bit smaller. R prime is equal to r. R prime dot is equal to r dot. R double dot prime is r double dot, right? Because when I take the derivatives in either frame for the r values, I get the same thing. Now what about over here? I already said theta prime is theta minus omega t. So if I take the derivative of theta prime dot, I get theta dot prime. Double hat rule is going to be equal to theta dot. And then, oh, that's minus. I did put minus. It just looks minus omega t. I take the derivative of omega t, so I get minus omega. So this says the angular velocity in the frame is the angular velocity in the non-frame minus that of the angular velocity of the frame. I know we're dealing with frames, things get a little crazy. And then finally I can take the second derivative, theta prime double dot, is going to be equal to theta double dot minus the derivative of that, which is 0. So the angular accelerations are the same. My reference frame is rotating at a constant velocity. Okay. Whew. So now let's go ahead and write the acceleration vector in normal coordinates, in normal polar coordinates. I can say r double dot 2-hat rule is going to be, now in polar coordinates you can't just take the derivative, right? Because I have these r hat, this is my r frame right here. I have r hat is that way and theta hat is that way. And so as the position moves, r hat and theta hat change. So they're not constant unit vectors. I have a whole video about how to find the acceleration polar coordinates, and I promise you I will link it down below. But if you did that, you would get this. Now we're only in polar coordinates right now. I get r double dot minus, what was it? Yeah, r theta dot squared r hat plus r dot theta dot r theta double dot. I'm out of the frame. No, I'm close. Plus r theta double dot plus 2 r dot theta hat. That's my acceleration in polar coordinates. Okay. Again, there's a video on that. So now let's find the acceleration in our new frame. So what I need to do is just to take, I don't need to replace r double dot. I don't need to replace r. All I need to do is replace theta dot with theta dot minus omega. And theta, I need to replace with theta minus omega t, but there's no thetas in the equation. So all I need to do is to put this in there. So let's write that, r triple hat here, double dot prime, r double dot prime. You like that? Triple hat. That's a triple hat. That's like, I call that a hat trick. It's a little soccer joke for you. Okay, so I get r double dot minus r, and then I have theta dot squared, so I need to put in, I'm really doing in the prime system, but I get theta dot minus omega. Theta dot minus omega, quantity squared, r hat, plus r, and then I have r theta double dot, which is just the same thing. I don't need to replace that. Theta double dot plus 2 r dot theta dot minus omega theta hat. Okay, let's just start mixing things up. I'm going to go ahead and write this, just part of it, negative r, and this is going to be theta dot squared minus 2 theta dot omega plus omega squared. That's this whole thing right there. Okay. And then if I do that, I get r double dot prime. I'm going to just write it out. I'm trying to think how much to write it out. Okay, what I want to do, I want to get my original r double dot vector out. So anything that's in the r double dot anyway that was in there before, like that, I'm going to keep. So I'm going to say r double dot minus, now here I get an r theta dot, that's that same term, r theta dot squared, right? I want that, so I'm going to keep that. That's this plus that. And then I'm going to say that's r hat. Now I still have this other stuff, so I have minus this times that, so I'm going to write that as plus 2 r theta dot omega, and then I have minus this times this, so minus r omega squared. And those are both in the r hat direction. Okay, so that's that whole term right there. This term, I'm going to write it as plus r theta double dot, and then I want it to look like this, so I want to get that term out. So plus 2 r dot theta dot, and I'm going to leave that as theta hat. And then the leftover stuff I get over here is going to be equal to, I have this term, 2 r dot minus omega. So I have minus 2 r dot omega theta hat. So you'll notice this stuff right here, that's just the acceleration. That's just the normal acceleration. And this is the extra stuff. Extra stuff. Looks like it's freezing. Is it? I hope this is going well, because I don't want to have to do this again. This is going to take a while. Okay, so now let's just combine these terms. I actually want to just because I know the answer, I'm going to take that term and then put these two terms together. So I'm going to write this as r double dot prime. That's just r double dot. And then here I'm going to actually factor out an r omega. No, I'm going to take this one and factor out a 2 r. Is that r dot? That was that term up there. Yeah. I'm going to factor out just a 2 omega. Okay, so I get plus 2 omega. So from this term, so that term is left with, I took out the 2 omega, so I have r theta dot, and then I'm going to factor out of this, so I have minus, and that goes with r hat, and then minus r dot theta hat. And then the other term I have left over is minus r. I should have omega squared. I messed up. Oh, there it is, right there. R. It is squared. I did do that. Minus r omega squared r hat. Okay, so there's my normal acceleration. I have this extra term, and I have that extra term. And so these, if I want to make them as a force, just like before, I just need to take the opposite of these. So this is actually what we call the Coriolis force, and this is the centrifugal force. So those are our fake forces in a rotating reference frame. So let me write that over here before I forget. F core, and this is just the, I guess this is a vector, and this is in 2D, right? F core is going to be negative, now I have to multiply it by the mass, negative 2m omega r theta dot r hat minus r dot theta hat, and then F centripetal is 2, no, not 2, m r omega squared r hat. So this points away from the center of the circle in the r hat direction, and this points in something different. So you'll notice here that if there's no angular acceleration for the object and no linear velocity, so this is a velocity term. If there's no velocity, then this term, there is no Coriolis force. So if you just have it stationary, then theta dot 0 and r dot 0, so the whole term goes away. But then that's your centrifugal force, which is the opposite of the acceleration for an object moving in a circle. I know it was tough, but that is pretty important. Okay, that's not how they normally derive it, because I derived it in a special case. I said that we're in 2 dimensions. It actually works in 3 dimensions. And I'm going to model this in just a second. But I do want to show you that it does indeed work, because a lot of times when you look up the Coriolis force, you see it looks a little bit different. And I want to show you that they're the same thing. So the Coriolis, and I wrote it down because I forget this. So the Coriolis force is often written negative 2m omega cross v. So this is the angular velocity vector of the frame, and that's the velocity in the frame. Okay, and that's the cross product. And then the centrifugal force looks really bad because, you know, it's hard to get this angular velocity squared. But we can do it as an actual vector, and it is, forgetting again, m omega cross r cross omega. Now, just to kind of placate and make people happy, and I will show you one more thing at the end, how these come about. It's just a tough derivation. It really is. I want to show you that in a flat surface like this, this works. This one I'm not going to do just because I don't want to do cross product twice. And I'm lazy, that's fine. So let's say that my velocity vector looks like this. The velocity in polar coordinates is r dot r hat plus r theta dot theta hat. And then I have a z component too. So let's imagine that my angular velocity is actually the vector in the z direction. So omega, I'm going to use omega, capital Omega, as omega z hat. So now I have cylindrical coordinates, so I can do this. I can do the cross product in cylindrical coordinates. So let's do omega cross v, and I'm going to leave off the mass. And we can use the matrix rule, so I can say r hat. This does work. Theta hat, z hat. I'm going to put down my components of omega, 0, 0, omega, lowercase omega. And then I can put my components of v, which are r dot, r, theta dot, 0. So let's do the cross product. So I'm going to expand about the r hat direction, and I get 0 times 0 minus omega times that. So I get minus omega r theta dot times r hat. Now I'm going to expand about this, and I get a negative term in front of that. So I'm actually going to go omega times r dot. So plus omega r dot theta hat. And then I'm going to expand about the z direction, I get 0. And so over here, you'll notice that I'm missing a 2. Oh, there's a 2 up there. Yeah, so I have 2m. If I multiply this by 2m, I do indeed get this. So that works. Okay, so you could do it with the, you could show up for that too, but I'm not going to. I'm going to do it in Python. Okay, let's jump into Python and model the motion of an object in a rotating frame. So what I'm going to do is draw the frame and pretend like it's rotating even though it's not actually. We're going to add in, we're going to throw a ball on a plane and add in the centrifugal and the Coriolis force, the centrifugal and the Coriolis force, and see what the motion of it's like. It'll be fun. And then I'll show you one more trick about derivatives in a rotating frame in general, how you can get this, but I'm not going to derive that because it's never intuitive to me. So let's jump over to WebVPython. Let's just build this from scratch and let's have a fun time doing it. That's the important part. So you know I'm going to use WebVPython. Let's just get started. I'm going to make just a disk just to pretend like that's my thing. Disk, it's going to be a cylinder. Position is going to be vector 0, 0, 0. It's at the order. No, I'm going to put it down. I'm going to have up and down as the y direction. So let's shift this down negative 0.1 just for sake. And then the axis is going to be vector 0, 0, 0.1. So it's going to be out that way. And then the radius is going to be equal to 1. Is that what I did before? I think I did a 1 radius of 1. Yep. Okay. Let's just run that. Make sure it's working. Okay, so there's my disk, and I can rotate it around. Now let's make a ball. And I want to take that ball and I want to throw it across the thing with the rotating object. So the ball is a sphere. Its position is going to be on the edge. So I'm going to say vector negative 1, 0, 0. And let's give it a radius of 0.1. Let's try that. Color equals color.yellow. And then make trail equals true. Run that. Okay, there's my ball. So now I need to put some other constants in there. I need my angular velocity. So let's say omega is vector 0, 0, 1. So the angular velocity, so it's rotating that way. My g vector, g is going to be vector 0, 0, negative 9.8. So again, I'm saying up and this is the z direction. That's the gravity. That's up and down. Okay. I need the mass of the ball. Ball.m. I don't actually need that. Is 0.1. I need the velocity of the ball. So I'm going to pick that. Ball.v equals vector 3, 0, 3. So I'm going to throw it up at an angle of 3 meters per second in the z component and 3 in the x component. Let's just throw it without gravity, without Coriolis force first, just to make sure things are working. Okay, t equals 0, dt equals 0.01, while ball.pos.z is greater than or equal to 0, because I don't know how long to run it, but I want to run it until it gets back down there. Rate 100, that just means only do 100 cycles per second, so it animates in real time. I'm going to calculate the acceleration. I'm going to write this as ball.a is just going to be equal to g. And so I could calculate the force. I'm not going to do that. I'm just going to calculate the acceleration, divide both sides by the mass. So that's just a free-falling ball that starts with initial velocity. I can use that to update the velocity, ball.v plus ball.a times dt. And again, I have not put in the Coriolis force or the centrifugal force. Yeah, centrifugal. And now I need to update the position, ball.pos plus ball.v times dt, update time. Run it. And there you can see, went across the thing. Pretty nice, right? Okay. So now let's go ahead and calculate the Coriolis and centrifugal force and add it in there. Let's just calculate that as an acceleration. A core, that's the Coriolis acceleration. Okay, so it's the force divided by the mass, so I don't really need the mass. So looking over here, the Coriolis force is -2 omega, which is the component of the velocity. I think I shouldn't have done it like that. Oh, no, wait, I'm sorry. I'm doing this one. -2 omega cross v. Yep, okay. So it's going to be -2, I don't need the mass, times the cross product of the vector omega across the vector v. So it's going to be omega and ball dot v. That's the Coriolis force. Let's calculate the centrifugal force. Now, again, you could ascend. Let's call it ascend. You could just say it's in the r hat direction, but I'm going to use the formula that we have up here. So it's the mass, which I'm going to leave off, the cross product of omega cross r. So cross omega cross r. Let's do that. But then I need to cross that. So I'm going to say cross omega cross r with r. So it's a cross product with omega. So it's a cross product of cross product. You can do that. No one cares. Python doesn't care. And now my acceleration is just going to be equal to plus a core plus a sin. So I'll get both of those accelerations in there. Remember, I threw the ball and it went straight across. Let's see what happens now. Nothing. Isn't that amazing? Because I made a mistake. R. Oh, that's why. So here I did the cross product with R, but there is no R. I'm going to use ball.pos. That is my R. There we go. So it did not go straight across. There's a great video of a rotating platform looking from the top, and people are tossing the ball back and forth. And if you look at it from the top, the motion of the ball will take this curved path if you're rotating with the platform, and that's because of that Coriolis force. And so that's kind of nice. It looks like it works. Okay, let's just try, just for fun, increasing the angular velocity and see what happens. And you'll notice it didn't even land on the platform. It got back down to 0, but it curved a lot more. So you can play around with that, but we can model the motion of this by looking at the acceleration in each time step and then using our normal rules for updating the velocity. If you want, I'm not going to do it. If you want, you could also add in vector arrows onto the ball to represent both the Coriolis force and the centrifugal force. Warning, they're very different sizes. You could make them the same size, but so you have to rescale those arrows. I'm not going to do that for now. I'm going to just keep it simple like this. And I am going to show you one more thing because I told you that I would, and I don't want to lie because this is already getting a long video. So the other way to get these derivations is to first derive this. That we can say that the derivative of a vector in a rotating platform, in a rotating frame, no, in a non-rotating frame, is equal to the derivative of the vector with respect to time in the rotating frame plus omega cross A. And so you can get the same things, and it looks like that from up here when you take the derivatives. And that's how you get those two things right there. But I'm not going to do that because this is difficult to derive. I've done it before, and it didn't really sit in my brain. I really like the two-dimensional version better because it matches up with our polar coordinates. So remember, I said polar coordinates derivation down below. I said I'd give that to you. And I think there was something else, but I forgot. So let's just stop there.